Welcome back, everyone. If you've been following our recent discussions, you know we've covered some exciting topics like scaling laws and Instruct GPOT. We've explored how models grow bigger, smarter, and more aligned with human input. But today, we're taking a new step forward.
Right. Today's paper brings a fresh perspective. We're moving beyond the usual scaling strategies in human alignment. It's all about making large models more efficient, and that's where BitNet comes in.
Exactly. BitNet is not just about making models perform well, it's about doing so sustainably. This episode focuses on how BitNet achieves competitive performance using one-bit quantization, reducing both memory usage and energy consumption.
And it's not just any quantization. We're talking about one-bit weights. That's a big leap from the 8-bit or even 16-bit models we've discussed before. It's a fascinating approach to training from scratch while maintaining high performance.
Absolutely. BitNet is a great example of how quantization-aware training, or QAT, can push the boundaries of AI scalability. It shows that even with lower precision, models can still scale well, similar to how traditional full-precision models do.
What's even more impressive is the energy efficiency. We're talking about up to 38x less energy compared to full precision models. That's huge, especially for real-world deployment where power and memory are major concerns.
Definitely. And the implementation is surprisingly simple, using BitLinear as a drop-in replacement for standard linear layers. This makes it compatible with existing architectures, making it easy to integrate and deploy.
I think our listeners will appreciate the practical aspects of BitNet too, not just the theoretical concepts. It's a significant step forward in making large language models both powerful and sustainable.
Exactly. We'll cover how BitNet's design brings together scalability, alignment, and energy efficiency in a way that feels accessible and actionable.
Sounds like we have a lot to unpack today. Let's dive into how BitNet changes the game for scalable AI.
Today, we are exploring the abstract of the study on BitNet, a novel one-bit transformer architecture designed for large language models. The abstract highlights key challenges, solutions, and outcomes. Let's break it down.
I'm ready. What's the main problem this study addresses?
The primary issue is the increasing size and energy consumption of large language models, making them hard to deploy efficiently. BitNet aims to tackle this by introducing one-bit weights, drastically reducing memory and energy requirements while maintaining performance.
One-bit weights. That sounds extreme. How do they work?
Exactly. One-bit weights represent a significant form of quantization, reducing the model's precision to a binary state, either +1 or -1. This makes computations faster and more energy efficient. BitNet uses a component called BitLinear to replace standard linear layers in transformers, allowing it to train from scratch with one-bit precision.
So, it's not just reducing precision after training, right?
Correct. Unlike many quantization methods that modify the model after training, BitNet incorporates one-bit quantization from the beginning. This is known as quantization-aware training, which adapts the model during training to optimize for low precision.
Interesting. But does this affect performance in any way?
Despite its reduced precision, BitNet achieves competitive results compared to traditional 8-bit and FP16 models. It retains accuracy while saving on memory and energy, making it more scalable.
That's impressive. How scalable is BitNet?
BitNet exhibits a scaling law similar to full-precision transformers, meaning it can effectively scale up to even larger models while keeping efficiency benefits intact. This makes it a promising solution for handling the growing demand for large language models.
Sounds like a major breakthrough in model optimization and sustainability.
Indeed, BitNet provides a pathway to creating more sustainable ACI models by cutting down both energy use and computational costs without compromising performance. That's a significant step forward in the field of large language models. Now that we've covered the abstract, let's delve a bit deeper into the foundations that led to this innovative development. In this section, we explore the rapid growth and impact of large language models. The introduction highlights how these models have transformed various tasks, but also outlines challenges in deployment due to their size, energy consumption, and inference costs.
I see. So, while these models are powerful, they're also quite resource intensive.
Precisely. As language models become larger, they require more memory bandwidth for processing model parameters, which creates bottlenecks. This not only affects performance but also increases the cost of deployment, especially in distributed systems.
And I assume this is where model quantization comes in as a potential solution.
Yes, exactly. Model quantization is a technique aimed at reducing the memory footprint and computational load of large-scale models. The introduction notes that quantization can make models more efficient while maintaining competitive performance.
I remember you mentioned quantization-aware training before. Is that discussed here too?
Yes, it is. The introduction distinguishes between traditional post-training quantization, which is applied after a model is trained, and quantization-aware training, which integrates reduced precision during the training process itself. While post-training quantization is simpler, it often leads to greater accuracy loss as precision decreases.
That makes sense. So, quantization-aware training is more effective for maintaining accuracy?
Exactly. However, it's not without its challenges. Quantization-aware training can be harder to optimize, particularly as model precision drops. The introduction emphasizes this as a critical hurdle for scaling large language models using lower precision.
I see. So, what's different about BitNet's approach to this challenge?
BitNet focuses on an extreme form of quantization binarization, which uses one-bit weights. While binarization has been explored in other neural networks like convolutional models, its application to large language models is novel. Preprint. Previous efforts mainly targeted tasks like machine translation or BRT pre-training, which are structured differently from unidirectional language models.
So, BitNet's use of binarization is a unique approach in the context of large language models?
Yes, that's right. By training the model to handle one-bit precision from scratch, BitNet aims to improve efficiency while ensuring stability during training. This is a significant leap because large language models are typically scaled much larger than other architectures.
That sounds promising. I suppose the introduction sets the stage for the technical solutions that BitNet offers.
Absolutely. The introduction wraps up by emphasizing BitNet's goal: to deliver an efficient, scalable solution for training large language models while preserving high performance. This lays the groundwork for the more detailed discussions that follow. Now that we've set the foundation with BitNet's overall architecture, let's move on to a key component that drives its efficiency. In this section, we focus on bitlinear, the core operation of BitNet's architecture. Bitlinear is responsible for replacing the conventional linear layers with binarized versions, allowing for one-bit precision during training and inference.
So, bitlinear is what makes BitNet achieve one-bit weights, right?
Exactly. It's the mechanism that enables the entire network to operate with binary weights. To achieve this, bitlinear uses the signum function to convert real-valued weights into either +1 or -1, centralizing them around 0 to maximize the capacity within the limited numerical range.
Centralizing the weights, does that help with training stability?
Good question. Yes, centralization before binarization reduces the L2 error between the real-valued and binarized weights, which helps maintain stability. A scaling factor, beta, is applied after binarization to fine-tune the representation, minimizing the variance loss caused by quantization.
I see. And what about activations? Are they also adjusted in this process?
Yes, activations are quantized as well, but to an 8-bit precision in this version of BitNet. The quantization uses an ABS-max approach, which scales the activations to fit within a specified range while preserving stability and efficiency.
So, it's not just about binarizing the weights, but also about ensuring activations align with a low-precision framework?
Precisely. This alignment is crucial because it ensures the model's components work cohesively within a low-precision environment. For example, the activations are clipped and scaled based on the maximum absolute value of the input, preventing overflow and maintaining consistency.
And does bitlinear handle the variance issue that arises from quantization?
Yes, bitlinear includes a layer norm operation before activation quantization to maintain the output variance at the same magnitude as full precision counterparts. This is vital for training stability, as it ensures the output distribution remains consistent, allowing BitNet to effectively handle one-bit transformations.
That's an interesting approach. So, bitlinear seems to be at the heart of BitNet's efficiency and stability.
Exactly. It allows BitNet to balance simplicity and performance while implementing binarization effectively across large-scale models. Now that we've explored the bitlinear mechanism, let's move on to how BitNet is trained to handle one-bit precision effectively. This section focuses on the training techniques used in BitNet to make the model converge effectively, despite the extreme quantization. The primary method used here is called the straight-through estimator, or STE.
I've heard of STE before. How does it help in this context?
Great! The STE is essential for bypassing non-differentiable functions during backpropagation. Since binarization involves the signum function, which is non-differentiable, STE allows gradients to flow through, approximating the gradient for binary operations and making the training process feasible.
So, it kind of cheats by allowing gradients to pass, even when the function isn't differentiable.
That's a good way to put it. It's a practical workaround to maintain gradient flow, which is critical for training one-bit models like BitNet. Without SISTE, the model would struggle to adjust weights effectively, leading to poor performance.
Makes sense. What about the optimizer states and gradients? Are they also quantized?
Not quite. While the weights and activations are quantized, the gradients and optimizer states remain in high precision during training. This ensures that updates are more accurate, preserving training stability and enabling better convergence.
I see. So, keeping the gradients in high precision helps stabilize the training?
Exactly. This mixed precision strategy ensures that the one-bit quantization doesn't compromise learning dynamics. Another aspect is the use of latent weights, which are maintained in high precision. These latent weights accumulate parameter updates and are binarized only during the forward pass.
That seems helpful, especially for maintaining accuracy in updates. What about learning rates? Do they play a role in this setup?
Yes, they play a crucial role. In fact, one of the challenges in training one-bit models is that small updates to the latent weights might not impact the binary weights significantly. To address this, BitNet uses a larger learning rate during training, which allows for quicker adjustments and helps the model converge faster.
So, the larger learning rate compensates for the lower precision of weights?
Precisely. While a high learning rate might cause divergence in full precision models, it actually benefits BitNet by accelerating convergence. This advantage is unique to the one-bit training approach, as it helps the model adapt more effectively to the binary state.
That's fascinating. It seems like the training process is quite tailored to handle the specific challenges of binarization.
Yes, that's the essence of BitNet's design, adapting every part of the training process to make one-bit precision work without sacrificing performance. With a solid understanding of how BitNet is trained, let's shift our focus to one of its most crucial advantages: computational efficiency. This section highlights how BitNet significantly reduces computational costs, making it more practical for large-scale language models. The main focus here is on the energy consumption of arithmetic operations and memory usage.
I'm curious, how much of an impact does one-bit quantization have on computation costs?
A substantial one. In BitNet, matrix multiplications, which are typically the most resource-intensive operations in transformers, become much more energy efficient. Since the weights are binarized, the multiplications become simpler, reducing energy consumption significantly. In fact, the energy cost of addition becomes the dominant factor, as the multiplication is reduced to a minimal level.
So, by using one-bit weights, BitNet mainly saves on the multiplication part of the computation?
Exactly. In traditional transformers, multiplication uses more energy than addition. But in BitNet, because the weights are binary, the multiplication is mostly replaced by simple additions and scaling factors. This dramatically lowers the energy needed for matrix computations.
That's a clever optimization. But what about memory usage? Does one-bit quantization help there too?
Yes, it does. Memory footprint is reduced because one-bit weights take up much less space compared to full precision or even 8-bit models. This not only makes BitNet more memory efficient, but also allows it to handle larger models within the same hardware constraints.
I see. Does BitNet use any specific techniques to further improve efficiency when running on hardware?
Great point. BitNet also incorporates techniques like group quantization, where weights and activations are divided into groups for parallel processing. This reduces synchronization overhead in distributed settings, making the model more scalable without adding extra communication costs.
So, group quantization helps in maintaining speed while keeping the computational load balanced across devices?
Exactly. It ensures that BitNet can efficiently leverage hardware capabilities, especially in distributed systems or model parallel setups. This is crucial for deploying large language models at scale while keeping energy costs low.
That's impressive. It sounds like BitNet is designed not only to be accurate but also to be highly efficient in real-world applications.
Yes, that's the goal. By minimizing both arithmetic energy and memory usage, BitNet becomes a more sustainable solution for handling large language models, making it a practical choice for deployment on various platforms. Having covered BitNet's training and efficiency, let's now explore how it performs under real-world conditions, starting with its setup and evaluation process. In this section, we'll discuss the experimental setup used to evaluate BitNet's performance and how it scales. BitNet was tested across various language models, ranging from 125 million to 30 billion parameters. The training data included a mix of popular language modeling datasets, such as the Pile and Common Crawl snapshots.
That's quite a broad range of model sizes. Was the setup similar to what's used for regular transformers?
Yes, to ensure a fair comparison, BitNet was trained using the same datasets and conditions as standard FP16 transformers. The key difference lies in the use of 1-bit weights, which required specific adjustments, like a larger learning rate, as we discussed earlier.
Got it. And how do they compare when scaling up?
This brings us to the inference optimal scaling law part. In traditional scaling laws, the loss typically decreases predictably as model size increases in time. BitNet follows a similar trend, showing that even with binarized weights, it scales effectively in terms of loss reduction, just like full precision models.
So, BitNet's scaling behavior is similar to that of full precision transformers, even though it uses 1-bit weights.
Exactly. The scaling law suggests that BitNet maintains competitive performance as the model size grows, which is significant because it proves that 1-bit quantization doesn't disrupt the model's ability to learn efficiently at larger scales.
Interesting. But does the scaling law apply to inference costs too?
Good question. Yes, it does. BitNet introduces what's called the inference optimal scaling law, which focuses on the relationship between model performance and inference energy consumption. Unlike traditional scaling laws that measure training compute, this law is more concerned with energy usage during inference, which is critical for real-world deployment.
That sounds useful, especially for understanding BitNet's efficiency during actual use.
Exactly. The inference optimal scaling law shows that BitNet achieves better performance per unit of energy consumed during inference compared to FP16 models. This makes it highly efficient not only in terms of memory and computation, but also in energy costs during deployment.
So, the law gives a clearer picture of BitNet's efficiency when it comes to real-world applications?
Yes, that's correct. It provides a more practical measure of how well BitNet can balance performance with resource usage, making it an attractive option for scaling large language models without excessive energy costs. Now that we've explored how BitNet scales and optimizes inference costs, let's move on to its real-world performance and stability. In this part, we examine BitNet's results on downstream tasks, which are designed to test the model's effectiveness beyond just language modeling. The evaluation includes tasks like zero-shot and few-shot performance on benchmarks such as HelloSwag, Winogrande, Winograd, and StoryClose.
That sounds like a comprehensive set of tests. How does BitNet perform compared to standard models?
Overall, BitNet shows strong performance across these tasks. In fact, its results are quite competitive with FP16 transformers, especially in zero-shot scenarios. The zero-shot scores of BitNet are comparable to 8-bit models, despite its 1-bit quantization.
Impressive. So, it manages to hold up even in tasks it hasn't been fine-tuned for?
Yes, that's one of the key highlights. While few-shot performance, where a small amount of task-specific data is provided, also shows promising results, BitNet tends to excel more notably in zero-shot settings. This suggests that the binarization doesn't compromise the model's generalization capabilities.
And how does it perform as the model size increases? Does it maintain accuracy across scales?
Exactly. The evaluation shows that BitNet's performance scales well with larger model sizes, maintaining accuracy across different task types. This is important because it demonstrates that 1-bit models can be effective for both smaller and larger models, making them versatile for various applications.
That's reassuring. But what about stability? I imagine training a 1-bit model could be more challenging.
Good point. The stability test is a critical part of this evaluation. In this test, BitNet is compared with FP16 transformers by varying the peak learning rates to see how well each model can converge during training.
I assume higher learning rates would be harder to manage, right?
Yes, typically, high learning rates can lead to divergence, especially in full precision models. However, BitNet shows better stability at higher learning rates. While FP16 transformers struggle to converge, BitNet benefits from the larger learning rate, enabling faster convergence without compromising accuracy.
So, it actually takes advantage of the higher learning rate to improve training speed?
That's correct. This is one of the strengths of binarized models like BitNet. They can adapt to more aggressive training strategies, making them not only efficient but also more stable during training.
It's impressive how BitNet balances both performance and stability in such a challenging setup.
Indeed, achieving this balance is what makes BitNet a promising solution for scalable and efficient large language models. With BitNet's performance and stability covered, let's now compare it with another common approach, post-training quantization. Post-training quantization, or PITQ, is a popular method where models are quantized after the full training process. It's simpler to implement and doesn't require modifying the training pipeline. However, this approach often leads to a significant drop in accuracy, especially at lower bit precisions.
So, PTQ is more about convenience than maintaining performance?
Exactly. PITQ is often used to quickly reduce the memory and computation footprint of models, but it has its drawbacks. BitNet, on the other hand, uses quantization-aware training, which incorporates the 1-bit precision from the start. This leads to better accuracy retention since the model adapts to the low precision during training itself.
That makes sense. But how do they compare in terms of performance on benchmarks?
BitNet consistently outperforms state-of-the-art PTQ methods like ABSMAX, SmoothQuant, GPTQ, and QuiP across multiple benchmark tasks. For instance, in weight and activation quantization, BitNet achieves higher zero-shot accuracy even when compared to 8-bit models quantized with PTQ.
So, BitNet not only keeps accuracy better but also achieves this with lower precision?
Correct. While PTQ methods may achieve reasonable results at 4-bit or higher precision, they struggle significantly at 1-bit. BitNet, however, is designed to handle 1-bit weights from scratch, allowing it to maintain competitive performance with far lower computational costs.
That's quite a difference. But is there any scenario where PTQ might still be preferred over BitNet?
Good question. PTQ might still be useful in scenarios where a pre-trained model needs a quick quantization solution and retraining isn't feasible. In such cases, PTQ can provide a faster path to deployment, albeit with some loss in accuracy and stability.
Got it. So, it's more of a trade-off between time and performance?
Exactly. BitNet, with its quantization-aware training, requires more initial effort, but the outcome is a more robust, energy-efficient model that performs well even at extreme levels of quantization. It's designed for longer-term benefits, especially when scaling models while keeping energy costs low. Now that we've seen how BitNet stacks up against post-training quantization, let's dive into the ablation studies that were conducted to understand its performance better. Ablation studies are a critical part of evaluating BitNet's design choices, helping to determine which components contribute most to its performance and stability. In this case, we looked at different aspects like activation quantization methods, layer normalization strategies, and other training stability techniques.
I assume these studies help clarify which parts of BitNet are most effective, right?
Exactly. The first set of ablations focused on activation quantization. BitNet uses ABSMAX for this purpose, but alternative methods like the elastic quantization function were also tested. ABSMAX proved to be more stable, enabling larger learning rates and better overall accuracy compared to elastic quantization.
So, ABSMAX seems to be a key factor in maintaining performance and stability.
Yes, it is. The ABSMAX method ensures that activations are scaled consistently, which contributes to BitNet's robustness, particularly in a low-precision setting. In contrast, the elastic function, though adaptive, didn't perform as well in stabilizing training at 1-bit precision.
What about the role of layer normalization? Was it tested in the ablations too?
Good point. Yes, different normalization strategies were tested. BitNet primarily uses sub-LN, which is a variant of layer norm tailored for low-bit models. The ablation compared sub-LN with pre-LN and another architecture called BMT, which was designed to improve the stability of binarized models.
And how did sub-LN perform compared to the others?
Sub-LN outperformed both pre-LN and BMT in terms of convergence and final accuracy. It's particularly well-suited for one-bit training because it maintains consistent variance across layers, a crucial aspect for training stability.
So, the choice of sub-LN really contributes to BitNet's ability to handle extreme quantization?
Precisely. The combination of sub-LN and ABSMAX has proven to be the most effective setup for BitNet, balancing both stability and performance. These ablation results underscore the importance of each design decision, showing that BitNet's architecture is optimized for handling the challenges of binarized training. After exploring the various components, performances, and insights from the ablation studies, it's time to wrap up our discussion with the key takeaways and future directions for BitNet. In conclusion, BitNet represents a significant step forward in scaling large language models with extreme efficiency. By introducing one-bit quantization as a core component from the start, it achieves competitive performance while drastically reducing memory footprint and energy consumption compared to traditional models. This makes BitNet not only scalable but also more sustainable in real-world deployments.
It's impressive how BitNet manages to balance efficiency and accuracy, even with such a drastic reduction in precision.
Absolutely. The success of BitNet shows that it's possible to maintain the effectiveness of large language models while pushing the limits of computational efficiency. The scaling law, strong downstream task performance, and enhanced training stability all support its viability as a solution for energy-conscious AI development.
So, what's next for BitNet? Are there any plans to improve or extend it further?
Yes, there are several exciting directions for future work. One of the main goals is to scale BitNet to even larger models with more training steps, to further explore its potential at higher levels of complexity. There's also interest in adapting the one-bit quantization approach to other model architectures, such as RetNet, which could broaden the applicability of BitNet's design.
That sounds promising. Are there any other aspects being considered for improvement?
Another area for future development is exploring lower precision for activations, not just weights. This could lead to even greater efficiency gains, although it comes with additional challenges in maintaining stability. There's also ongoing research into integrating BitNet with other acceleration techniques, like speculative decoding, to enhance both training and inference speed.
It's exciting to see how BitNet can evolve and potentially influence the design of other models as well.
Indeed. The innovations introduced by BitNet have opened up new possibilities for creating high-performance, low-energy models, making AA more accessible and sustainable across various applications. That wraps up our discussion on BitNet and its innovative approach to one-bit quantization. We've covered how it manages to maintain performance, scale effectively, and significantly reduce energy consumption.
Yes. And we also explored how its quantization-aware training allows for stable learning from scratch, which is pretty impressive for such low-precision models.
Absolutely. BitNet's simple implementation and compatibility with existing architectures make it an impactful step toward more sustainable AI models.
It's been a great discussion. BitNet truly shows how efficiency can be achieved without sacrificing scale or performance.
Agreed. We hope you found this episode insightful. Thank you for joining us today and for your continued support.
Yes, thanks for listening, everyone. We're excited to keep exploring the latest in AI with you.